Dear students, we were discussing about modeling of three-phase transformers. In the last class, we have seen two connections. Those are grounded Y connection and delta grounded Y connection. In this class, we will see few more connections. Before going to those connections, let's see a review of some transformer modeling matrices. So we have seen for this case, if you want to convert your line to neutral voltages to line voltages, your conversion matrix is D. So, line to neutral voltages to the line voltages, they can be converted using matrix D, and this matrix D is given by this matrix here. And then to convert line voltages to line to neutral voltages, you have this conversion matrix W, and this W is given here. If you want to convert your delta phase currents to the line currents, so these are the delta phase currents, and if you want to convert into line currents, the conversion matrix is K, and the K is given by this matrix here. In case if you want to convert line currents to the delta currents, your conversion matrix is L, and L is given here. And if you want to convert again this line currents to the delta currents, your conversion matrix is M here. However, the difference between these two cases are like this: if your zero sequence currents absent in your configuration, then you need to use this L matrix here, and if zero sequence currents present, so if the zero sequence current present, then you need to use this matrix here. So, if you see the difference between IDABC and IABC, this is like this. So, these are say three phase windings, and these are your lines. So, this is say A phase, B phase and C phase. So, this current will be IA, this is IB, and this is IC. This current will be ID AB, this will be ID BC, and this will be ID CA. So, which will basically flowing like this. So, these IDAB, IDBC and IDCA, these are nothing but IDABC currents, and these IA, IB and IC, they will be nothing but your IABC currents. Then we have seen this grounded Y by grounded Y connection in the last class. Before that, we have seen modeling of three-phase transformers, and we have seen that three-phase transformers can be modeled using ABCD parameters. Those are represented as AT, BT, CT, DT. These are your secondary terminals of the transformer. These are your primary terminals of the transformer. Here the voltages are V, capital ABC. So, here line to neutral voltages I can represent. So, here the voltages will be VLN ABC, capital letter for primary, and secondary side they will be VLN small ABC. Currents on primary side IABC, capital letters, and on secondary side it will be IABC small letters. So, this is your IA, IB, IC. Here also this is IA, IB and IC. And then to represent this in ABCD parameter terms, so primary side voltage is written in terms of secondary voltage and secondary currents. Then you get this A and B parameters of transformer, and when we write your primary side currents in terms of secondary side voltages and secondary side currents, we get these C and D parameters. And we have derived these A, B, C, D parameters for grounded Y by grounded Y connection in the last class, and the vector group of this transformer is YG, YG0. This 0 represent phase displacement between primary and secondary voltages, and we have got this expression here. So, if you compare these equations with your standard equations of ABCD parameter, this is your A parameter, this is your B parameter, and this is your D parameter, because there is no term related to VLN ABC into this expression here. That is why your C is 0. So, we can easily see your AT parameter will be nothing but AV, and this AV matrix we have seen that it is anti, anti, anti diagonal entries, and non-diagonal entries are 0. So, you can easily write it like this. It will be NT into your unity matrix, because NT I can take it common. So, it will be unity matrix like this. So, I can say it will be NT multiplied by U. Similarly, BT is having your AV matrix, which is again NT 0 0 0 NT 0 0 0 NT, which is AV matrix here. And then ZT ABC matrix, we have seen that this ZTA, ZTB and ZTC diagonal entries, and off diagonal entries are 0 here also. Now, if I consider ZTA is equal to ZTB is equal to ZTC is equal to ZT, so in that case I can take this ZT common out from this one. So, it will we can write it like this, NT multiplied by ZT into your unity matrix. So, in this case you can see that A parameter can be converted into NT multiplied by U, B parameter can be converted NT multiplied by ZT multiplied by U, where this ZTA, ZTB, ZTC are the leakage impedances of the transformer. They are generally same in case of 3-phase transformer. They may be different in case of 3 different transformers if you are connecting them in grounded Y fashion. And then this AI matrix, so DT matrix we have seen, it is AI, and AI nothing but 1 by NT 0 0 0 1 by NT 0 0 0 1 by NT. And so, in this case also we can take NT common out. So, 1 by NT and your unity matrix. So, DT parameter can be represented like this, and your C parameter, so CT parameter will be 0 0 0 3 by 3 in size. So, this was the derivation for grounded Y by grounded Y connection. In case of delta grounded Y, we had got these expressions, and if you can compare them with standard equations of transformer modeling, we can see that this is your A parameter, this is your B parameter, and this is your D parameter. So, your AT parameter will be nothing but your W matrix multiplied by AV, and we have seen that this W matrix is given by this matrix here. So, in this case your W I can keep as it is, and AV matrix is nothing but NT diagonal entries. So, in that case NT can be taken out common, and then it will become unity matrix. So, this will be just NT multiplied by W, and in case of BT it will be W multiplied by AV is again diagonal entries NT with off diagonal 0 entries, and your leakage impedance matrix is ZTA, ZTB and ZTC diagonal entries with off diagonal entries are 0. And so in this case also, if again ZTA equal to ZTB equal to ZTC, we can have this ZT common out. So this matrix will become equal to NT, I can take it common out from this one, ZT I can take common out from this one, multiplied by W. And then your CT matrix will be K multiplied by AI, where this K matrix is given by this term here. So it will be K multiplied by AI is 1 upon NT 0 0 0 1 upon NT 0 0 0 1 upon NT. So it will be equal to 1 by NT into your K matrix. Sorry, this is your D matrix, and your C matrix will be equal to 0 0 0 0 0 0 0 0 0 3 by 3 size. So for delta grounded Y connection, that is DYG, because Y is grounded and it is 11, means it consists of 30-degree phase shift between primary and secondary quantities. For those, you can see that your A parameter is given by NT multiplied by W here, your B parameter is given by NT multiplied by ZT multiplied by W here, and your D parameter is given by K divided by NT, and C parameter is 0. So these two connections we had seen in the last class. Now go for third connection, which is ungrounded Y and delta connections. So in this case, primary is ungrounded Y and secondary is delta connected. So in this case, let's see, these are your 3 transformers. And this is your secondary side. All the impedances we are referring to the secondary side. So this is your impedance in one phase, impedance in another phase, impedance in third phase, and this we are connecting in delta fashion. So we can just connect it like this with this, and this winding I can connect it to the first winding. So this will give us our delta connection. And if you see the primary winding, so this is one terminal here, second terminal, third terminal, and since we are connecting it in Y fashion, we need to take this neutral connection. However, in this case it is ungrounded Y, means this neutral will not be grounded. So this is your A terminal, B terminal, C terminal, HV side. So this should be IA current, IB, but it is capital letters, and IC. This terminal will be small a, this terminal will be small b, and this terminal will be small c. So this current is IA, IB and IC, but represented by small letters here. This impedance is ZTAB because it is between A and B phase. This is ZTBC and this is ZTCA. This terminal voltage or voltage across this winding VTAB, this is VTBC and this is VTCA. This voltage on primary side will be VAN, VBN and VCN. The currents are like this. So this current I can say IBA because it is flowing from B and A terminal. This will be ICB and this will be IAC. Now if you write the expression for voltages which are basically these winding voltages, so I can just say your voltage VAN, VBN and VCN they will be just related by your turns ratio, and this turns ratio can be calculated. In this case it will be NT turns ratio will be equal to VLN, because primary is Y connected, HV rated voltage, divided by, since secondary is delta connected, you need to take line to line voltages which are across the winding. So LV, and you need to take rated voltage of LV side, line to line voltage. So this will be equal to NT 0 0 0 NT 0 0 0 NT, and this will be VTAB, VTBC and VTCA, means these terminal voltages here, this voltage and this voltage will be related to VAN, VBN, VCN by just turns ratio. So we can write this in short form. So these voltages will be V line to neutral, because these voltages are line to neutral voltages, ABC capital letters will be equal to this matrix, we know that it is AB matrix, multiplied by this is VTABC matrix. Let us say this is expression number 1. Another equation I am getting from terminal voltages of this transformer. So I can say terminal voltage VAB, or we can write in opposite way. So I can say VTAB will be equal to VAB plus ZTAB into IBA. So basically this current here, this current multiplied by this impedance will give me impedance drop, and plus this voltage VTAB. So VAB, so voltage here plus this impedance drop will give me VTAB. Similarly, I can say VTBC will be equal to VBC plus ZTBC into ICB, and third equation VTCA will be equal to VCA plus ZTCA into IAC. Now if you write them in matrix format, so these voltages are nothing but VTABC, so these are VTABC, which will be equal to, these are nothing but line to line voltages on secondary side, so these are VLL small abc plus this matrix of impedances Z T ABC matrix multiplied by these currents. If you observe, they are ID ABC because these are nothing but your delta currents. So let us say this is expression number 2. So from 1 and 2, so you have got this expression number. Okay, so I am saying this is your 2 and this is expression number 1. So these two expressions can be written like this, and if you put this expression into this, I will get this expression here. So I can say VL and ABC will be equal to AV multiplied by VT ABC is given by this term here, which I am putting it here. So basically this is your this term. So if you multiply this AV inside bracket, so it will be AV multiplied by VLL ABC and then AV multiplied by ZT ABC multiplied by ID ABC. Now if you see the standard form of equation, so standard form of A and B parameter is like this. So here we need line to neutral voltages, here also we need line to neutral voltages, and here we need line currents. So if you observe this form here, this is line to line voltages which need to be converted into line to neutral, and this part is delta phase currents which need to be converted into line currents. So we have seen the conversion matrices. So these line to line voltages can be written into line to neutral voltages by multiplying it with D. So V line to line will be equal to D multiplied by V line to neutral ABC, and this ID ABC can be written as L multiplied by I ABC. So ID ABC can be replaced by L multiplied by I ABC. So now we have got in standard format. So here also we are getting line to neutral voltages on both the sides, and then here we are getting line currents. So this will be your AT parameter. So your AT parameter will be AV multiplied by D matrix, and your B parameter will be AV multiplied by JT ABC multiplied by L. So let us simplify it. So we have got this A and this is your B. So A is AV multiplied by D. AV we have seen it is diagonal entries NT, and D matrix is given by this expression here. So in short form I can write, from this I can take NT common out, so it will just remain unity matrix. So unity matrix multiplied by some matrix will be, it will be same, so it will be just NT multiplied by D here, and your BT parameter we have seen it is AV multiplied by ZT ABC multiplied by L, which is here. AV is again diagonal entries with NT, ZT ABC is again diagonal entries of all this leakage impedances of 3 phases, and this is your L matrix. So in this case also, if your ZT AB is equal to ZT BC is equal to ZT CA is equal to ZT, I can take it common out. So this I can write, from this I can take NT common out, so it will remain unity matrix. From this, if this condition getting satisfied, I can take ZT common out, so this also remain unity matrix, and this is your matrix L. So NT multiplied by ZT multiplied by your L matrix is nothing but your B parameter. Now to get C and D parameters, we have seen that we need to take current relations into account. So if you observe, I can easily write your IA current will be nothing but your IBA current divided by NT, your IB current will be nothing but ICB divided by NT, and your current IC is nothing but ICA divided by, or IAC divided by NT. And in short form I can just write it like this: IABC, these are nothing but line currents, so I can just say IABC will be nothing but your AI matrix, because this I can just write it like this, it will be IA, IB and IC will be nothing but 1 by NT, 1 by NT, 1 by NT diagonal entries and 0 0 0 off diagonal multiplied by IBA, ICB, IAC. Okay, so this is your IABC in short form. This matrix we know that we call it as AI, and this is IDABC because these are delta phase currents. So this is nothing but your IDABC. So if you compare this with your standard, so I will just take this on next slide. So call it as expression number 1. So expression number 1 I have taken on this slide here, and if you compare this with standard equations in terms of C and D parameter, so here if you compare C parameter is 0, however to get the D parameter we need line currents here, but we are having delta currents here. So these delta phase currents can be converted into line currents by using this L matrix, and these delta phase currents can be written as L multiplied by IABC. Okay, now we are getting in standard format. So C will be 0 and your D matrix will be equal to AI multiplied by L. So AI we have seen it is diagonal entries 1 by NT, and this is your L matrix. So from this I can take NT common out, so it will be 1 by NT remaining unity matrix multiplied by L matrix. So unity multiplied by L will be just L matrix. So 1 upon NT multiplied by L. So this is your D parameter here. We also calculated a capital A parameter and capital B parameter, and these capital A and capital B parameters are defined at like this, which are basically used to calculate line to neutral voltages on secondary side in terms of primary side voltages and the load currents. So generally load currents are known, primary voltages are known because those are applied voltages. Then load terminal voltages will be calculated using these capital A parameter and capital B parameter. Now to calculate it, we can use this expression here, which you have derived in earlier slides, and what we need on left hand side is VLN ABC. So we can bring this on left hand side and all the remaining quantities on right hand side. So in this case I can say VLN ABC will be equal to VLN, or here it's multiplication by AV multiplied by your D, it will remain as it is, will be equal to VLN capital ABC minus AV multiplied by ZT ABC multiplied by L into I ABC. If you see the standard format, we need only VL and ABC on this side, so we can just multiply this by D inverse multiplied by AV inverse. So if you multiply D inverse multiplied by AV inverse to this term, it will get cancelled out. So it will be just VLN ABC. This term will get multiplied with D inverse multiplied by your AV inverse into VLN ABC. This term also will get multiplied with D inverse and AV inverse. This AV is as it is, and ZT ABC into L into I ABC. So this AV inverse and AV will get cancelled out, and we have seen that whenever there is D inverse term we get, we need to replace by W. So it will be W multiplied by AV inverse into VLN capital ABC minus your D inverse, means you need to replace by W into Z T ABC multiplied by L into your I ABC. So you can see that if you compare with standard equation, this will be nothing but your capital AT term, and this will be nothing but your capital BT term. Now capital AT term is W multiplied by AV inverse, and capital BT term is W multiplied by ZT ABC multiplied by L term. So if you write them explicitly, so this is your W matrix and this is your AV matrix and its inverse. If you see the inverse of this part, it will be just 1 by NT, because they are only diagonal entries, so it will be just 1 by NT, 1 by NT, 1 by NT. Of diagonal entries will be 0 if you take the inverse of this matrix. So from this I can take 1 by NT common out, which will get multiplied by W. So AT I can just write it like this, and in case of BT also, this is your W and ZT ABC. So if you consider ZT AB equal to ZT BC equal to ZT CA equal to say ZT. So in that case these three entries will be equal, which can be taken out common. So it will be in that case ZT multiplied by your W matrix multiplied by your L matrix. So in this case it will be ZT multiplied by W multiplied by L. So we have seen ungrounded Y by delta connection. Now let us see your last connection, that is delta delta connection, and in this case I am considering vector group which is DD0, means phase displacement between primary and secondary quantities will be 0. So they will be connected like this. So you are having this transformer 1, transformer 2, and this is transformer 3. The impedances are referred on secondary side, so I should represent them here, and these are the terminals. Now we have seen that to connect delta we can connect them like this. So this is delta connection on secondary side, and this is your delta connection on primary side, and this terminal will be taken out as a capital A terminal, this will be capital B terminal, this will be capital C terminal. Similarly, this will be small a terminal, this will be small b terminal, and this will be small c terminal. Therefore, this voltage will be VAB, this voltage will be VBC, this voltage will be VCA, this voltage will be VTAB, this will be VTBC, this will be VTCA, this impedance is ZTAB, this impedance ZTBC because it is connected between B and C phase, ZTCA, and this current we are considering IBA, this current is ICB, and this current is IAC. On this side this will be IA, IB and IC, capital letters for primary side, and this will be IA, IB and IC, small letters for secondary side. Now in this case also we can write two expressions here. First is based on your turns ratio. So VAB, VBC and VCA, they will be related to your VTAB, VTBC and VTCA voltages by just turns ratio. Therefore, the diagonal entries will be NT, and we know that this is nothing but line to line voltages. So VLL ABC will be equal to, this is your AB matrix, and these are VTABC voltages. So in short form I can represent this by VLL, this by AV and this by VTABC. I can just say this is expression number 1, and one more relation I can write in terms of terminal voltages and the voltages across the winding VTAB. So VTAB will be equal to voltage VAB plus ZTAB multiplied by IBA current. VTBC will be nothing but VBC plus ZTBC into ICB, and VTCA will be equal to VCA plus ZTCA into IAC. And these three equations also we can write in short form like this. So these on left hand side I can represent it by VTABC is equal to, these three voltages will be nothing but line to line voltages on secondary side. So VLL ABC plus your impedance matrix ZT ABC multiplied by these currents which are ID ABC, because these are delta phase currents, and this I can write expression number 2. So, if we take these two equations on next slide, so we have got these two equations here. So, VLL ABC is equal to AV into VT ABC, which was actually our first equation. So, this was our first expression, and this was our second expression, which I represented here. Now, I can put this VT ABC into this expression here. So, after putting this, I will get this expression. So, VT ABC I have inserted into this expression here. So, in that case VLL ABC will be equal to AV multiplied by VLL plus AV into ZT ABC. And then to convert this into line to neutral voltages, we need to multiply whole expression by W. So, here if I multiply by W, I will get this. This also will get multiplied W, and this also will get multiplied with respect to W. And on this side, I will get VLN ABC, because W multiplied by V line to line voltages will be VLN ABC, and these terms are as it is. Now, let us take these terms on. Okay, so here this VLL ABC can be written as D multiplied by VLN ABC. Similarly, these currents ID ABC can be written as M multiplied by IABC. So, this ID ABC currents can be written as M multiplied by IABC. So, if you compare with standard equations, so this must be your A T parameter, and this must be your small BT parameter. So, BT parameter. So, if I take these parameters on next slide, so your AT parameter we have seen, it is W multiplied by AV multiplied by D. Out of this AV can be represented by diagonal entries of NT, and those can be taken it out. So, this can be written as NT multiplied by your W matrix multiplied by your D matrix, because this term I can take common out. So, this is your W and this is your D. So, it will be NT multiplied by W multiplied by D, and in case of BT we are having W multiplied by AV multiplied by ZT-ABC multiplied by M. So, this is your W matrix, this is AV, this is ZT-ABC, and this is nothing but your M matrix. So, if ZTAB is equal to ZTBC equal to ZTCA, so this is actually ZTBC and ZTCA. If they are equal to say ZT, in that case from this we can take ZT common out, from this we can take NT common out, keeping W and this M matrix. But we have seen that if these impedances are equal, your M matrix is actually equal to your L matrix. So, in this case we can easily write, so we can take this NT out, ZT common out, and this is nothing but your M matrix, or this is nothing but your W matrix multiplied by this is nothing but your M matrix. However, since ZTABC and ZTBC, ZTCA they are equal, I can represent this M matrix by L here. So, this is how we can get A parameter and B parameter. To get C and D parameter, we have to take the current relations into account. So, in this case I can write IAB will be equal to 1 by NT into IBA, IBC will be equal to 1 by NT into ICB. ICA will be equal to 1 by NT into IAC, and if you write them in short form, so these are nothing but your delta currents. So ID capital ABC is equal to, this will form your AI matrix because this will consider as the diagonal entries of AI matrix, and then these are nothing but ID ABC, which are delta phase currents in secondary winding. Now, if you compare this with our standard equation, so standard equation is like this: IABC is nothing but your C parameter CT into VLN small abc plus your DT into IABC. So, here this term is not there, so we do not have to worry, but here we need line currents, and here also we need line currents. So, what we can do, we can multiply both the matrices by K. So, it will be K multiplied by ID ABC, which will be equal to, since it is just diagonal entries, I can just exchange the position of K. So, instead of writing it in first, I can write this as second matrix. So, K multiplied by ID ABC, and this is nothing but your IABC. So, K multiplied by IDBC is nothing but IABC, which will be equal to AI multiplied by, this is also I small abc. So, let us take this expression on next slide. So, we have got this expression here IABC, which is equal to AI multiplied by IABC. So, if you compare with standard equation, C will be 0 because in this expression there is no term related to VLN ABC, and your DT will be nothing but AI matrix, and this will be equal to, since diagonalities we can take common out. So, it will be 1 by NT into U matrix, which is identity matrix. So, we have got A, B, C, D parameters, and as I told you, we are also interested in calculating capital A and capital B parameters, and those capital A and B parameters we need in this format. So, we need VLN small abc, which is secondary side voltage, which is written in terms of primary side voltage, which is VLN capital ABC minus your BT parameter into secondary side current IABC. So, we want actually expression to be in this format to get capital AT and capital BT parameters. So, from your first equation which you have derived earlier slide, what we can do, we can take this term on left hand side and remaining terms on right hand side. So, if you do this, so this term I am taking on left hand side. So, here I have taken this, and the remaining terms on right hand side, which are basically this. Now, we want to eliminate this term here, because on left hand side we want only VLN ABC here. So, what we can do, we can multiply this whole expression by D inverse. So, whole expression will be multiplied with D inverse multiplied by AV inverse multiplied by your W inverse. So, if you multiply this whole expression by this particular term here, so here this will get cancelled out. So, only VLN ABC will remain on left hand side. This will get multiplied with this term. So, here there will be D inverse, AV inverse multiplied W inverse will remain. Here W and AV will get cancelled out with AV inverse multiplied by W inverse. So, only D inverse term will remain here. So, D inverse ZT ABC as it is, NEM as it is. Then we have seen that wherever D inverse is coming will be replaced by matrix W. So, D inverse we are replacing with matrix W. So, here also this D inverse will be replaced by matrix W. So, we can see that we have got in standard format. So, on this side is secondary voltage in terms of primary voltages and load currents. So, this will be your capital A T parameter and this will be capital B T parameter. Let us see what are these parameters. So, capital A T parameter, which is W multiplied by AV inverse multiplied by D, and AV inverse we know that it is 1 by NT, 1 by NT, 1 by NT. From that I can take NT common out, multiplied by your W matrix multiplied by your D matrix. So, if you do the multiplication of W and D matrix, I will get this expression here, or else I can directly write, just write it will be 1 by NT, which is coming from AV inverse multiplied by W multiplied by D here, and then from this side it is, if I am considering ZTAB equal to ZTBC equal to ZTCA equal to ZT, I can take ZT common out from this expression, keeping W and M as it is. But we have seen that whenever this condition is getting satisfied, W will be replaced by L. So, BT parameter will be ZT multiplied by W multiplied by L, where all these matrices are defined it here. So, in summary of this lecture, two more connections we have seen. Those are ungrounded Y by delta connections whose vector group is YD1, and then finally we have seen delta delta connection whose vector group is DD0. So, here we complete modeling of 3-phase transformers. In the next class we will see one example of typical distribution transformers, and for that example we will calculate ABCD parameters. We will also see one more connections which is called as open Y open delta connections, which is also widely used to serve 3-phase as well as single phase loads. Thank you.